Let me ask you something that has kept the greatest minds in physics awake at night for over 100 years. Take a magnet, any magnet, a refrigerator magnet, a bar magnet, the magnet inside your phone's speaker. It has a north pole and a south pole. Now cut it in half. What do you get? You get two smaller magnets, each with its own north pole and its own south pole. Cut those in half again. Same thing. Two more complete magnets, each with both poles. You can keep cutting forever, down to the atomic level, and you will never ever isolate a single magnetic pole by itself. Never just a north. Never just a south. Always both, locked together in an eternal partnership that nothing in the known universe can break apart. Now here is what makes this deeply strange. Think about electricity. You can absolutely have a single positive charge sitting alone in space. A proton does exactly that. You can have a single negative charge by itself. An electron does that every single day. Electric charges come in singles. They are perfectly happy existing alone. But magnetic poles, they refuse to be separated. They insist on coming in pairs, always without exception, in every experiment ever performed, in every observation ever made, in every corner of the universe we have ever examined. Why? Why this fundamental difference between electricity and magnetism? Why does nature allow electric monopolies but seemingly forbid magnetic ones? This asymmetry is not just a quirky fact of nature. It sits at the absolute heart of modern physics. It connects to the deepest questions we can ask about reality. It connects to why electric charge comes in exact packets. It connects to the first fraction of a second after the Big Bang. It connects to whether all the forces of nature were once unified into a single superforce. It connects to why the universe exists in its current form at all. Today, we are going on what might be the deepest journey we have ever taken into the fundamental structure of reality. We are going to explore a mystery that has fascinated, frustrated, and driven physicists for generations. We are going to follow a trail that leads from ancient Greece to the most powerful particle accelerator ever built. We are going to encounter one of the most beautiful mathematical proofs in all of physics, a proof that says magnetic monopolies must exist. And then, we are going to confront the disturbing fact that despite decades of searching with increasingly sophisticated technology, nobody has ever found one. Along the way, we will discover how the search for monopolies accidentally gave birth to one of the most important theories in cosmology. We will hear about a single tantalizing event detected on Valentine's Day in 1982 that still has no explanation. We will learn how materials in laboratories have produced something that behaves exactly like a magnetic monopole, proving the mathematics works even if nature refuses to create the real thing at a fundamental level. And we will wrestle with questions that go beyond physics into philosophy. Does mathematical beauty guarantee physical reality? How long should science search for something that theory demands but experiment denies? When does absence of evidence become evidence of absence? If you are fascinated by the deepest mysteries of our universe, this is going to be a journey worth taking. Hit that subscribe button because what we are about to explore will fundamentally change how you think about magnetism, about symmetry, about the origin of the universe, and about the limits of human knowledge itself. Let us begin at the beginning, and the beginning, in this case, is ancient. Humans have known about magnetism for thousands of years, long before we had any framework for understanding it. The ancient Greeks discovered that certain stones found near the city of Magnesia in what is now Turkey had a remarkable property. These stones, called lodestones, could attract iron. They could make iron filings dance and jump across gaps. They seemed to possess an invisible force that reached out through empty space and grabbed onto certain metals. Thales of Miletus, one of the earliest Greek philosophers, encountered these stones around 600 years before the Common Era. He was so struck by their behavior that he concluded they must possess souls. That was the only framework available to him. Something that could reach out and affect other objects at a distance without touching them seemed alive. It seemed to have agency and intention. For thousands of years, magnetism remained in this realm of the mystical and unexplained. The Chinese discovered around the 1st century that lodestones, when suspended freely, would always align themselves in a particular direction. They invented the compass, one of the most transformative technologies in human history, without ever understanding why it worked. They knew that a magnetized needle would point north. They used this knowledge to navigate vast distances across land and sea. But the why remained completely mysterious. The first truly scientific investigation of magnetism came from William Gilbert, an English physician, in the year 1600. Gilbert published a book called De Magnete, which translates to On the Magnet. In this remarkable work, Gilbert performed careful experiments and came to a revolutionary conclusion. The Earth itself, he argued, is a giant magnet. The compass needle does not point towards some celestial object or some mystical force. It aligns with Earth's own magnetic field. The planet we live on is in essence an enormous bar magnet with a North Pole and a South Pole. Gilbert also noted something critical that would echo through the centuries. He observed that every magnet, no matter its shape or size, always had 2 poles. He could never create a magnet with only one pole. Break a magnet, and each piece immediately has both poles. This was noted, recorded, but not deeply questioned. It was simply accepted as how magnets worked. 2 centuries later, the relationship between electricity and magnetism began to reveal itself, and with it, the strangeness of the missing monopole became more apparent. In 1820, a Danish physicist named Hans Christian Ørsted made a discovery that changed physics forever. He was giving a lecture demonstration about electricity when he noticed that a compass needle near a wire carrying electric current would deflect. Electricity and magnetism, which had been studied as completely separate phenomena for centuries, were connected. An electric current creates a magnetic field. This was not a small discovery. This was the moment that unified 2 apparently different forces of nature into aspects of a single phenomenon. Ørsted's discovery set off a frenzy of investigation. If electricity could create magnetism, could magnetism create electricity? Michael Faraday, working in England, showed that yes, a changing magnetic field could induce an electric current in a wire. These discoveries back and forth, electricity creating magnetism and magnetism creating electricity, painted a picture of deep interconnection between these 2 forces. Faraday was not a mathematician in the formal sense, but he was a genius of visualization. He invented the concept of field lines, those imaginary lines that trace out the direction and strength of a field at every point in space. And he noticed something profound about magnetic field lines. Electric field lines have clear beginnings and endings. They start on positive charges and end on negative charges. You can trace an electric field line from its birth on a proton to its death on an electron. But magnetic field lines do not have beginnings or endings. They form closed loops. Always, every magnetic field line curves around and reconnects with itself, forming a continuous, unbroken circuit. There are no starting points, there are no ending points, no sources, no sinks. If magnetic monopolies existed, they would be exactly those missing starting and ending points. A north monopole would be a source, a point where magnetic field lines begin and stream outward. A south monopole would be a sink, a point where magnetic field lines converge and end. But Faraday's observations showed no such points exist. The field lines always close upon themselves. Then came James Clerk Maxwell, and the mystery deepened. Maxwell, a Scottish physicist working in the 1860s, accomplished something extraordinary. He took all the known laws of electricity and magnetism, the discoveries of Coulomb, Ampere, Faraday, Ørsted, and many others, and unified them into 4 elegant mathematical equations. These 4 equations, known as Maxwell's equations, describe everything about classical electromagnetism. Every radio wave, every beam of light, every magnetic field around a wire, every electric field around a charge, all described perfectly by 4 compact mathematical statements. But here is what matters for our story. Maxwell's equations contain a deep and disturbing asymmetry. The first equation, called Gauss's law for electricity, says that electric field lines can diverge from sources. Those sources are electric charges. Electric monopolies exist, and the equation acknowledges them. The equation for magnetism, however, Gauss's law for magnetism, says something very different. It says the divergence of the magnetic field is 0. Everywhere, always, this is a mathematical way of saying there are no magnetic charges, no sources of magnetic field lines, no sinks, no magnetic monopolies. The other 2 Maxwell equations show similar asymmetry. Faraday's law describes how changing magnetic fields create electric fields. Ampere's law, as modified by Maxwell, describes how electric currents and changing electric fields create magnetic fields. But there are no magnetic currents in these equations, no flow of magnetic charge. The whole framework is built on the assumption that magnetic monopolies do not exist. Maxwell himself recognized this asymmetry and found it aesthetically troubling. He noted in his writings that if magnetic charges did exist, his equations would become beautifully symmetric. Each equation would have a perfect mirror image. Electricity and magnetism would be perfect duals of each other, interchangeable through a simple rotation. The equations without monopolies work perfectly to describe every experiment ever performed. But they carry this nagging imperfection, this broken symmetry, like a face that is beautiful but slightly asymmetric in a way you cannot stop noticing. For decades after Maxwell, this asymmetry was simply accepted. The equations worked. They predicted new phenomena. They led to the discovery of radio waves, the development of electrical technology, the understanding of light itself as an electromagnetic wave. Nobody could argue with their success. And if they said magnetic monopolies did not exist, well, that was just how nature was. Then, in 1894, Pierre Curie made a statement that would slowly change the conversation. Curie, already famous for his work on magnetism and crystallography, pointed out something simple but important. There is no fundamental physical law that forbids the existence of magnetic monopolies. Their absence from Maxwell's equations is not derived from any deeper principle. It is simply put in by hand, based on the observation that nobody has ever found one. But observation is not the same as prohibition. Just because we have not found something does not mean the universe forbids it. Curie argued that physicists should actively search for magnetic monopolies rather than simply assuming they do not exist. Curie's argument was noted, but did not create an immediate revolution. The physics community was focused on other things. The quantum revolution was beginning. Relativity was about to reshape our understanding of space and time. Magnetic monopolies remained a curiosity in the background. Until 1931. Until Paul Dirac. Paul Adrien Maurice Dirac was one of the strangest and most brilliant physicists who ever lived. He was phenomenally quiet in person, speaking only when he had something precise and important to say. His colleagues joked that the unit of conversational output for Dirac was 1 word per hour. But when he wrote physics, the results were stunning. His equation for the electron, published in 1928, predicted the existence of antimatter years before it was discovered. When Carl Anderson found the positron in 1932, it was exactly what Dirac's equation demanded. This established Dirac's reputation as someone whose mathematical predictions should be taken extremely seriously by experimentalists. In 1931, Dirac turned his attention to the magnetic monopole, and what he produced was one of the most elegant arguments in all of theoretical physics. He did not just show that monopoles were allowed by quantum mechanics. He showed that their existence would solve a mystery that had no other known solution. Here is the mystery Dirac was addressing. Why is electric charge quantized? What does that mean? It means that every electric charge ever measured is an exact integer multiple of a fundamental unit, the charge of the electron. You can have 1 electron's worth of charge, or 2, or 3. You can have 1/3 in the case of quarks, which combine to always give integer multiples anyway. But you never find a charge of 1.7 electron units, or 0.4 electron units. Never. Charge comes in exact packets, like money comes in exact cents. You cannot have half a cent. You cannot have half an electron's charge. But why? Nothing in classical electromagnetism requires this. Maxwell's equations work perfectly fine for any amount of charge, integer or not. There is no mathematical reason why charge should come in discrete units, rather than taking any continuous value. This quantization of charge is simply an observed fact with no deeper explanation. It is like a law with no lawmaker. Dirac showed that magnetic monopolies provide the lawmaker. His argument went like this. In quantum mechanics, particles are described by wave functions, mathematical objects that encode all the information about a particle's state. These wave functions must satisfy certain consistency conditions. They must be single-valued, meaning that if you take a particle on a path that loops back to its starting point, the wave function must return to its original value. Dirac considered what would happen to a charged particle's wave function in the presence of a magnetic monopole. He found that consistency, the requirement that the wave function be single-valued, imposes a strict relationship between the electric charge and the magnetic charge. Specifically, the product of the electric charge and the magnetic charge must equal an integer multiple of a fundamental constant. This is the Dirac quantization condition. And here is the thunderbolt. This condition does not apply to just one particle. If even a single magnetic monopole exists anywhere in the universe, then the quantization condition must hold for every electric charge everywhere. One monopole, anywhere, at any time in the history of the cosmos, forces all electric charges to be integer multiples of a fundamental unit. It explains charge quantization. It provides the missing reason. It turns an unexplained fact into a derived consequence. Think about what this means. A single particle, potentially on the other side of the observable universe, potentially created in the first fraction of a second after the Big Bang and never seen since, would be responsible for the fact that your phone works, that chemistry follows its rules, that atoms are stable. One particle, everywhere at once in its influence, dictating the rules that every charged particle in existence must follow. Nothing else in physics has this kind of reach. Nothing else can claim such universal influence from such a singular existence. Dirac did not claim monopolies definitely existed. He was too careful a physicist for that. What he showed was that they are consistent with quantum mechanics and that their existence would explain something otherwise inexplicable. He provided a powerful reason to believe in them and an even more powerful reason to search for them. Dirac's argument also introduced a mathematical construction that would become important later, something called the Dirac string. To make the mathematics of a monopole work in the framework of standard electromagnetism, Dirac had to attach an infinitely thin, infinitely long tube of magnetic flux to the monopole, like an infinitely thin wire running from the monopole off to infinity. This might sound like a problem. If you need an infinitely long wire attached to your particle, that seems pretty conspicuous. But Dirac showed that this string is physically undetectable. No experiment can detect its presence. It is a mathematical convenience that has no physical consequences. Different choices of where to put the string give exactly the same physical predictions. The string is pure gauge, as physicists say, an artifact of the description rather than a feature of reality. But the monopole at the end of the string? That would be very much detectable, very much real, very much consequential. After Dirac's paper, the magnetic monopole was elevated from an aesthetically pleasing symmetry argument to a genuine prediction of quantum mechanics. The search intensified. But before we follow that experimental hunt, we need to understand what a magnetic monopole would actually be like as a physical object. What would its properties be? How would it behave? What would happen if you held one in your hand, assuming you could? First, let us talk about mass. Based on Dirac's quantization condition, we can estimate how strong the magnetic charge of a monopole would be. The minimum magnetic charge, the smallest possible, turns out to correspond to a coupling strength much larger than the electric charge. A monopole would interact with magnetic fields about 68.5 times more strongly than an electron interacts with electric fields. This makes monopoles much more strongly coupled to electromagnetic fields than familiar charged particles. As for mass, Dirac's theory does not predict a specific mass. The monopole could, in principle, be any mass. But there are other theoretical considerations. If monopoles are fundamental point particles, their mass might be relatively modest, perhaps in the range accessible to particle accelerators. If they are the topological objects predicted by grand unified theories, which we will discuss shortly, they would be extraordinarily heavy, far beyond the reach of any accelerator we can currently imagine. How would a monopole behave? In many ways, it would be the magnetic mirror image of an electric charge. An electric charge placed in an electric field feels a force and accelerates. A magnetic monopole placed in a magnetic field would feel a force and accelerate. An electric charge moving through a magnetic field curves in a circle. A magnetic monopole moving through an electric field would curve in a circle. The symmetry is perfect. If a monopole passed through a coil of wire, it would induce a very specific electrical signal. As it approached, a current would build. As it passed through, the current would spike. After it left, a permanent change in current would remain if the coil were superconducting. This last part is crucial. In a superconducting loop with zero resistance, the passage of a monopole would leave an indelible signature. A permanent step change in the current flowing through the loop. This is exactly what detectors look for. A monopole moving through ordinary matter would also be distinctive. Because its coupling to electromagnetic fields is so strong, it would rip electrons from atoms much more violently than ordinary charged particles. It would leave a trail of ionization far more intense than anything else of similar speed. This intense ionization would make it stand out dramatically in particle detectors. Now imagine the full symmetry that would emerge if monopoles existed. Currently, Maxwell's equations have electric charges and electric currents as sources, but no magnetic charges or magnetic currents. If monopoles exist, you add magnetic charge density and magnetic current density to the equations. The four equations become perfectly symmetric. For every statement about electricity, there is a mirror statement about magnetism. Change the word electric to magnetic and vice versa, and the equations map onto themselves. This is called electromagnetic duality, and it is breathtaking in its mathematical beauty. This duality would mean something profound. It would mean that the distinction between electricity and magnetism is not fundamental. It is a matter of perspective, of convention, of which charges you choose to call electric and which you choose to call magnetic. You could rotate your definitions, calling what we currently call electric charge a mixture of electric and magnetic charge, and the physics would be unchanged. Electricity and magnetism would be revealed as two faces of a single, deeper phenomenon with a symmetry even more perfect than we currently appreciate. This beauty is seductive. Many physicists feel in their bones that such symmetry must be real, that nature would not get so close to perfection and then stop. But feeling is not evidence, and evidence is what we need. Let us advance to 1974, because in that year, the theoretical landscape for monopolies changed dramatically. Two physicists working independently, Gerard 't Hooft in the Netherlands and Alexander Polyakov in Russia, made a discovery that transformed the monopoly from a possibility to what appeared to be a certainty. They were not looking for monopolies specifically. They were working on grand unified theories, attempts to unify all the non-gravitational forces into a single framework. And what they found shocked them. To understand what 't Hooft and Polyakov discovered, we first need to understand what grand unified theories are trying to do. In our current understanding of particle physics, there are three fundamental forces acting on matter at the subatomic level. The strong nuclear force holds quarks together inside protons and neutrons. The electromagnetic force governs interactions between charged particles. And the weak nuclear force is responsible for certain types of radioactive decay. These three forces have very different strengths and very different ranges. They seem quite distinct from each other, but there are hints of a deeper unity. The electromagnetic force and the weak force have already been successfully unified into what is called the electroweak force. This unification was achieved in the 1960s and 1970s by Sheldon Glashow, Abdus Salam, and Steven Weinberg. At high enough energies, the electromagnetic force and the weak force are indistinguishable. They are two aspects of a single electroweak force. Only at lower energies does this unified force break apart into the distinct electromagnetic and weak forces we observe in everyday physics. Grand unified theories take this idea one step further. They propose that at even higher energies, the strong force also merges with the electroweak force. All three become aspects of a single, grand, unified force. The energy scale at which this happens is enormous, about 10 to the power of 15 times the energy of the proton mass. This is far beyond anything our particle accelerators can reach directly. But it is not beyond the conditions that existed in the very early universe, a tiny fraction of a second after the Big Bang. In the earliest moments of the universe, when temperatures and energies were high enough, there would have been only one force. As the universe expanded and cooled, this unified force would have undergone a phase transition, similar to how steam condenses into water or water freezes into ice. During this phase transition, the single force broke apart into the three separate forces we observe today. The strong force separated first, and then later the electromagnetic and weak forces distinguished themselves from each other. Now here is where monopolies enter the picture. Phase transitions in everyday physics often produce defects. When water freezes into ice, you get cracks, bubbles, and grain boundaries where different crystal domains meet. When a ferromagnet is cooled below its transition temperature, you get domain walls separating regions magnetized in different directions. These defects arise because the transition cannot happen simultaneously and identically everywhere. Different regions undergo the transition slightly differently, and where these regions meet, defects form. The same is true for the phase transition of the unified force in the early universe. Different regions of space would break the symmetry in different directions, in the abstract internal space of the theory. Where these regions met, topological defects would form. And 't Hooft and Polyakov showed that among these topological defects would be magnetic monopoles. But these are not the simple Dirac monopoles, point particles with magnetic charge. These are far more complex objects. A 't Hooft-Polyakov monopole has internal structure. It is not a point, but a tiny, incredibly dense knot in the fabric of the unified force field. At its center, over an incredibly small region of space, the full unified force still reigns. The symmetry has not broken there. It is as if a tiny bubble of the original, unified early universe has been preserved, frozen in place, while the rest of the universe moved on and differentiated into the three separate forces. The size of this core is determined by the unification energy scale and is incredibly small, far smaller than a proton. But the mass it contains is enormous by particle physics standards. A single gut monopole would have a mass of about 10 to the power of 16 times the proton mass. In more familiar units, this is roughly 1/100th of a microgram. That might sound tiny in everyday terms, but for a single particle, it is absolutely colossal. A proton weighs about 10 to the power of -24 grams. A gut monopole weighs 10 to the power of -8 grams. The monopole is 100 trillion times heavier than a proton. It is heavier than many bacteria. A single fundamental particle, heavier than a living cell. And here is the critical point that 't Hooft and Polyakov demonstrated. These monopoles are not optional features of grand unified theories. They are mandatory. Any theory that unifies the forces through a phase transition with the mathematical structure required by grand unification will inevitably produce monopoles. You cannot have guts without monopoles. They are woven into the mathematical fabric of these theories as surely as quarks and electrons. This was simultaneously thrilling and deeply troubling. It was thrilling because it upgraded the monopole from a theoretical possibility to an almost inevitable prediction. If grand unified theories are correct, and we have many independent reasons to think they are at least on the right track, then monopoles exist. Period. They were created in the early universe. They carry within them a frozen memory of the moment when the forces separated. They are relics of the most extreme conditions that ever existed in our universe. But it was deeply troubling because of what came next. Simple calculations of how many monopoles the gut phase transition should produce gave a horrifying answer. The production of monopoles in the early universe is governed by what is called the Kibble mechanism, named after Tom Kibble, who worked it out in the 1970s. The basic idea is this: the phase transition that separates the forces cannot happen in perfect synchrony across the entire universe. Different regions of space choose different orientations for the symmetry breaking, different directions in the abstract mathematical space. The maximum distance over which regions can coordinate is limited by the speed of light and the age of the universe at that time. Regions farther apart than this distance undergo the transition independently. Where regions with different orientations meet, the fields must interpolate between the different choices. In some configurations, this interpolation inevitably creates a topological defect, a monopole. The density of monopoles produced depends on the density of independent regions, which depends on the horizon size at the time of the transition. When you plug in the numbers for the gut phase transition, which would have happened at about 10 to the power of -30, 6 seconds after the Big Bang, the result is catastrophic. The calculation predicts roughly 1 monopole per horizon volume at that time, which translates to a monopole density today, comparable to the density of ordinary matter. In other words, there should be approximately as many monopoles as there are protons in the universe. Now remember that each monopole is 10 to the power of 16 times heavier than a proton. If there are as many monopolies as protons, the total mass in monopolies would be 10 to the power of 16 times greater than the total mass of all ordinary matter. The universe's total mass energy density would be dominated overwhelmingly by monopolies. The expansion of the universe would have proceeded completely differently. The universe would have recollapsed long ago. Stars, planets, people, none of it would exist. The universe as we know it would be impossible. This is the monopole problem. It is not a minor difficulty. It is a full-blown catastrophe for the combination of grand unified theories and standard Big Bang cosmology. And it demands a solution. One possible solution is that grand unified theories are simply wrong. Perhaps the forces never unify. Perhaps there is no gut phase transition and no gut monopolies. But this feels like throwing the baby out with the bathwater. Guts explain too many other things: the quantization of charges within a generation of particles, the relative strengths of the forces, the possibility of proton decay, the patterns of particle masses. Abandoning guts just because they predict monopolies seems premature. Another possible solution is that the Kibble mechanism overestimates monopole production. Perhaps the phase transition happened more smoothly than calculated. But careful analysis shows this is difficult to achieve without fine-tuning the theory in unnatural ways. The solution that the physics community eventually embraced is far more radical, and it came from a young physicist named Alan Guth. In 1979, Alan Guth was a postdoctoral researcher at the Stanford Linear Accelerator Center, struggling with the monopole problem among other issues in cosmology. He had been working with Henry Tye on calculations of monopole production in guts, and the numbers were deeply disturbing. There were too many monopolies, way too many, and nobody could figure out how to get rid of them. Then Guth had an insight that would transform cosmology. What if, after the gut phase transition produced all those monopolies, the universe underwent a period of incredibly rapid exponential expansion? Not the steady expansion we observe today, but a brief, violent, explosive expansion that doubled the size of the universe every tiny fraction of a second. If this happened for long enough, any monopolies that had been produced would be diluted to essentially zero density. Take a box full of monopolies and stretch it by a factor of 10 to the power of 26 in every direction, and the average number of monopolies per observable universe drops to essentially zero. This is cosmic inflation. It was invented specifically to solve the monopoly problem. Guth published his paper in 1981, and it sparked a revolution in cosmology that continues to this day. What makes inflation so compelling is that it does not just solve the monopole problem. It simultaneously solves two other major puzzles in cosmology that had been bothering people for years. The horizon problem is the question of why the universe looks so uniform in every direction, even though distant regions appear to have never been in causal contact. Inflation solves this because before inflation, those regions were in contact, close enough to equilibrate, and then inflation stretched them far apart. The flatness problem is the question of why the geometry of the universe appears to be so close to perfectly flat. Inflation solves this because exponential expansion drives any initial curvature toward flatness, just as inflating a balloon makes its surface appear flatter and flatter. Three problems solved by one mechanism. This is powerful evidence that inflation actually happened. But notice the profound irony. Monopolies predicted by guts motivated the invention of inflation. Inflation then explains why we cannot find monopolies. The theory that says monopolies must exist also provides the mechanism that hides them from us. It is as if the universe created a magnificent treasure and then built an infinitely large vault around it. The treasure is real, but you will never reach it. if inflation is correct. Then the number of monopolies in our observable universe might be 0, or 1, or perhaps a handful scattered across billions of light-years of space. In any case, far too few to ever detect with current technology by simply waiting for one to wander past a detector. This does not mean the search is hopeless. Monopolies could potentially be produced in other ways. High-energy collisions in particle accelerators might create monopole-anti-monopole pairs if there is enough energy available. The energy required depends on the monopole mass, and if monopoles are light enough, it might be within reach of current or future colliders. There might also be monopoles that are lighter than the gut scale, predicted by other theories. And there is always the possibility that our estimates of inflationary dilution are slightly off, and a few primordial monopolies remain within detectable range. The experimental search for magnetic monopolies has been one of the longest and most determined campaigns in physics. Let us trace its history. The first serious searches began in the 1960s using cosmic ray detectors. The idea was simple. If monopolies exist in the cosmos, some of them might be zipping through space as cosmic rays, occasionally passing through the Earth. If one passed through a detector, its intense ionization would leave an unmistakable signal. Early searches used nuclear emulsion plates, photographic materials that record the passage of charged particles as tracks. A monopole would leave an exceptionally thick, dark track. None were found. Throughout the 1970s, the search expanded. Researchers looked for monopolies trapped in materials. The idea here is that monopolies, being so strongly magnetically charged, would stick to ordinary matter. If monopolies had rained down on Earth over billions of years, some might be embedded in rocks, in ocean sediment, in lunar samples brought back by the Apollo missions. Researchers passed samples through sensitive magnetometers that could detect the magnetic field of a trapped monopole. Moon rocks were tested. Deep ocean manganese nodules were tested. Ancient minerals were tested. Nothing. But the most famous episode in the history of monopole detection happened on a winter day in Palo Alto, California. In 1982, Blas Cabrera, a physicist at Stanford University, had built what was then the most sensitive monopole detector in the world. It was conceptually simple, but technically extraordinary. A single loop of superconducting wire, cooled to near absolute zero, carrying a persistent current. In a superconductor, current flows forever without resistance, and any change in the magnetic flux through the loop causes a precise, permanent change in that current. If a magnetic monopole passed through the loop, it would change the flux by exactly 1 quantum of magnetic flux, causing a current jump of a precise, predictable amount. Nothing else would produce this exact signature. Cabrera's detector ran for months, recording data continuously. The apparatus was shielded from external magnetic disturbances. It sat quietly, waiting. On February 14, 1982, Valentine's Day, the detector recorded an event. The current in the superconducting loop jumped by exactly the amount predicted for a magnetic monopole passage. Exactly. Not approximately. Not close enough. Exactly. The jump corresponded to precisely 1 Dirac magnetic charge passing through the loop. The data was clean. There were no other disturbances, no power glitches, no mechanical vibrations, no temperature fluctuations. Just one perfect, textbook clean signal that looked exactly like what a magnetic monopole should look like. Cabrera was cautious. He published the result as a candidate event, not a discovery. He pointed out that a single event could be a statistical fluke, an unknown systematic error, or some exotic noise source that coincidentally mimicked a monopole. He called for independent confirmation, and he immediately began building a larger, more sensitive detector to either confirm the result or determine that it was an anomaly. The physics world buzzed with excitement. Headlines appeared around the globe. Could this be it? Could the holy grail of particle physics have been found in a small laboratory in California? The larger detector was built. It had multiple loops, providing redundancy and the ability to track a monopole's trajectory. It was even better shielded. It was more sensitive. And it ran for years. It never detected another event. No other experiment anywhere in the world detected a monopole either. The single Valentine's Day event remained alone, unique, unrepeated. To this day, nobody has convincingly explained what caused it. It was not a failure of the equipment, because the equipment worked flawlessly before and after. It was not a cosmic ray, because normal cosmic rays produce a different signal. It matches the monopole prediction perfectly, but one event is not enough for a discovery in physics. The standard threshold is 5 sigma significance, meaning the probability of the signal arising from chance must be less than 1 in 3.5 million. One event does not meet this threshold. The Valentine's Day monopole remains one of the most tantalizing unexplained events in experimental physics. It is a single data point that refuses to be either confirmed or dismissed. It sits in the literature, haunting the field, a reminder that the universe might have whispered an answer once and then gone silent. After Cabrera's tantalizing near miss, the search for monopolies continued with increasingly large and sophisticated experiments. The macro experiment, whose name stands for Monopole, Astrophysics and Cosmic Ray Observatory, was a massive detector that operated from 1989 to 2000 in the Gran Sasso National Laboratory in Italy, deep under a mountain to shield it from ordinary cosmic rays. Macro used 3 completely independent detection methods simultaneously. It had liquid scintillator tanks that would light up when an ionizing particle passed through. It had streamer tube tracking detectors that could trace a particle's path. And it had nuclear track detectors, plastic sheets that would be permanently damaged by the passage of a heavily ionizing particle. A monopole would trigger all 3 systems in a consistent way. In over a decade of operation, Macro detected no monopoles, but it set the most stringent limits yet on how many monopoles could be passing through the Earth. Meanwhile, at the Large Hadron Collider at CERN, the most powerful particle accelerator ever built, a dedicated experiment called MOEDAL began operating in 2010. MOEDAL, which stands for Monopole and Exotics Detector at the LHC, takes a different approach. Instead of looking for monopoles drifting through space, it looks for monopoles created in the incredibly energetic collisions between protons at the LHC. When protons smash together at nearly the speed of light, the energy of their collision can create new particles according to Einstein's famous equation relating energy and mass. If monopoles have a mass low enough, some fraction of these collisions might produce monopole-antimonopole pairs. MOEDAL uses 2 main detection strategies. First, it deploys stacks of plastic nuclear track detectors around one of the LHC's collision points. A monopole, being so heavily ionizing, would blast a distinctive fat track through these plastic sheets, unmistakable from the thin tracks of ordinary particles. Second, it uses aluminum trapping detectors, blocks of aluminum placed near the collision point. If a monopole is produced and slows down enough to stop, it would be trapped in the aluminum by its strong magnetic attraction to the aluminum nuclei. The aluminum bars are then removed and passed through a very sensitive squid magnetometer to check for a trapped magnetic charge. As of the latest published results, MOEDAL has found no monopoles. But each run of the LHC pushes the limits further, ruling out monopolies with masses below increasingly high thresholds. If monopolies are light enough, the LHC should eventually find them. If they are too heavy, we will need a more powerful machine. There is another elegant way to search for monopolies that uses the entire galaxy as a detector. This approach was first articulated by Eugene Parker and gives what is called the Parker bound. The argument goes like this. Our galaxy has a large-scale magnetic field that threads through interstellar space. This field is relatively weak, about a few millionths of a Gauss, but it extends over tens of thousands of light years. If magnetic monopolies exist in the galaxy, this magnetic field would accelerate them, just as an electric field accelerates electric charges. As the monopolies accelerate, they drain energy from the galactic magnetic field. If too many monopolies are present, they would drain the field completely on a timescale shorter than what is needed to regenerate it. But we observe that the galactic magnetic field exists. It has not been drained away. Therefore, the number of monopolies in the galaxy must be below a certain limit. This limit, the Parker bound, constrains the flux of monopolies to be less than about 10 to the negative 15 per square centimeter per second per steradian. This is an incredibly tiny number. It means that even a detector the size of a football field would wait many years between monopole passages, on average. The Parker bound can be strengthened by considering the magnetic fields of galaxy clusters and other cosmic structures. These refined limits make the experimental challenge even more daunting. But they also tell us something important. If monopolies exist in the quantities needed to be cosmologically interesting, they should have been detected by now. Their absence is consistent with inflationary dilution. Neutron stars provide another astrophysical laboratory for constraining monopolies. Neutron stars have extremely strong magnetic fields, trillions of times stronger than Earth's magnetic field. If monopolies drifted through the galaxy, some would be captured by neutron stars through gravitational and magnetic attraction. Once captured, they would be accelerated by the neutron star's intense magnetic field, gaining enormous kinetic energy that would eventually be dissipated as heat. This heating would be detectable as thermal emission from the neutron star. We observe neutron stars that appear to be very cold, with surface temperatures below what monopole heating would produce if monopoles were abundant. This places additional limits on the monopole density in the galaxy, complementing the Parker bound with an independent constraint. The IceCube Neutrino Observatory at the South Pole provides yet another window. IceCube consists of thousands of optical sensors buried deep in the Antarctic ice, watching for flashes of light produced by particles passing through the ice. A monopole moving at relativistic speeds through ice would produce a characteristic pattern of Cherenkov radiation, light emitted when a particle moves faster than the speed of light in a medium. The pattern from a monopole would be different from that of any other known particle because of the monopole's unique ionization properties. IceCube has searched for these signatures and found none, placing limits on the flux of relativistic monopoles. Taken together, the experimental evidence paints a consistent picture. Every method of searching, direct detection with superconducting loops, cosmic ray searches with massive underground detectors, accelerator production at the LHC, astrophysical limits from galactic magnetic fields and neutron stars, ice-based detectors at the South Pole, all give the same answer. No monopolies found, with increasingly stringent limits on how common they could be. This is either because monopolies do not exist at all, or because they are so rare that our searches have simply been too small and too short. Inflationary cosmology predicts the latter. If the universe inflated by the enormous amount needed to solve the horizon and flatness problems, the dilution of monopolies would be so extreme that we might need to survey a volume millions of times larger than our observable universe to find even one. But in 2009, something remarkable happened that reinvigorated the whole field. It did not involve fundamental monopolies, but it proved that the mathematics works. In certain exotic crystalline materials called spin ices, physicists discovered excitations that behave in every measurable way like magnetic monopolies. Spin ices are materials where the magnetic atoms are arranged in a specific geometric pattern called a pyrochlore lattice. In this arrangement, the atomic magnets are frustrated, meaning they cannot all simultaneously satisfy the forces between them. This frustration leads to a peculiar ground state, where the magnetic moments organize according to a rule analogous to the rule governing hydrogen atoms in water ice, which is why they are called spin ices. The key materials are dysprosium titanate and holmium titanate. In these materials, the magnetic atoms sit at the corners of tetrahedra, and in the lowest energy state, two magnetic moments point into each tetrahedron and two point out. This is the ice rule. When you add energy to this system by heating it or applying a magnetic field, you can create excitations that violate the ice rule. A tetrahedron might end up with three moments pointing in and one pointing out. This violation carries what is effectively a magnetic charge. It is a source of magnetic field lines within the material. And the remarkable thing is that this effective magnetic charge is deconfined, meaning it can move freely through the crystal, independent of any partner charge. It behaves exactly like a magnetic monopole. These are not fundamental monopoles. They are emergent phenomena, collective behaviors of many atoms working together. A single atom is not a monopole. But the coordinated behavior of the crystal lattice produces excitations that carry magnetic charge, obey the Dirac quantization condition, produce Coulomb-like force laws between each other, and in every measurable respect are perfect analogues of fundamental monopolies. This discovery was reported in the journal Nature in 2009, with experiments by groups in France, Germany, and England confirming the monopole-like behavior through neutron scattering and other techniques. The researchers could measure the density of monopolies, their motion, their interactions, all matching the predictions of Dirac's theory adapted to the lattice setting. What does this mean for the search for fundamental monopolies? Several things. First, it confirms that Dirac's mathematical framework is correct. The theory works. Nature is capable of producing magnetic charges, at least as emergent phenomena. The underlying mathematics is validated. Second, it gives experimentalists practice detecting and characterizing monopole-like signatures. Third, it demonstrates that the concept of magnetic charge is not merely a theoretical abstraction, but can be realized physically. And fourth, it raises the tantalizing question of whether what we call fundamental particles might themselves be emergent phenomena in some deeper substrate. But let us be clear about what spin-ice monopolies are not. They are not fundamental particles. They exist only within the crystal and cannot be extracted from it. They do not carry true magnetic charge in the fundamental sense. They do not explain charge quantization. They cannot solve the monopoly problem in cosmology. They are analogues, models, demonstrations of principle. The search for fundamental monopolies continues unaffected by their discovery, though inspired by it. Let us now turn to string theory and what it has to say about monopolies, because string theory has its own rich relationship with these objects. String theory, the framework that proposes all particles are actually tiny vibrating strings or higher dimensional objects called branes, naturally contains magnetic monopolies. In fact, string theory provides multiple ways to realize monopolies. Some arise as particular winding configurations of strings. Others arise as D-branes, higher dimensional objects on which strings can end, wrapped around compact dimensions of the extra spatial dimensions that string theory requires. In string theory, the electromagnetic duality between electric and magnetic charges gets elevated to a fundamental symmetry called S-duality. This duality says that a string theory with a strong coupling constant is mathematically equivalent to another string theory with a weak coupling constant, where the roles of electric and magnetic charges are exchanged. What appears as a heavy, strongly coupled monopole in one description appears as a light, weakly coupled fundamental particle in the dual description. This is profound. It suggests that the distinction between ordinary particles and monopoles is not absolute, but depends on which description you choose to use. In one description, electrons are fundamental and monopoles are heavy composite objects. In the dual description, monopoles are fundamental and what we call electrons are heavy composite objects. Neither description is more correct than the other. They are two equivalent ways of describing the same physics. This duality has been incredibly powerful in advancing our understanding of quantum field theory and string theory, even independent of whether actual monopoles are found in nature. It has allowed physicists to solve previously intractable problems by switching to the dual description where the problem becomes easy. It has revealed deep connections between seemingly different theories, and it has reinforced the expectation that monopoles are not just allowed, but essential to the full structure of theoretical physics. Let us take a step back now and consider something called the Rubikov-Kalin effect, because it reveals just how exotic and dangerous a gut monopole would be. In 1982, Valery Rubikov and independently Curtis Kalin discovered something startling about the interaction between gut monopoles and ordinary matter. They showed that a proton passing close to a gut monopole would be catalyzed to decay. Normally, protons are extraordinarily stable. The proton lifetime is at least 10 to the power of 34 years. More than a trillion times the current age of the universe. For all practical purposes, protons never decay. The processes that would allow proton decay require energies close to the gut scale, which are not available under normal circumstances. But the core of a gut monopole is special. Remember, at the center of a gut monopole, the full unified force still persists. The symmetry that is broken everywhere else remains intact there. And in this tiny region of intact unification, processes that are forbidden by the broken symmetry become possible. A proton venturing near the core of a monopole enters a region where the strong force and electroweak force are unified, where the distinction between quarks and leptons dissolves, and where proton decay can proceed at an enhanced rate. The cross-section for this catalyzed decay is enormous by particle physics standards. It is similar to the geometric cross-section of the proton itself, meaning that a proton that passes within about a proton radius of the monopole core will almost certainly decay. The proton would break apart into lighter particles, positrons and pions, releasing energy. This effect has implications for the search for monopoles. If a gut monopole passed through ordinary matter, it would catalyze the decay of nuclei along its path, producing a trail of positrons and pions that would be unmistakable in a detector. Some experiments have searched specifically for this catalysis signature without finding it, placing further limits on monopole abundance. The Rubikov-Kalin effect also means that gut monopoles, if they could somehow be captured and concentrated, would be extraordinarily dangerous objects. They could destabilize ordinary matter, causing nuclei to disintegrate at a catastrophic rate. A collection of monopoles inside a star could catalyze nuclear decay and alter stellar evolution. Some theoretical papers have explored whether monopoles captured by neutron stars or white dwarfs could affect their evolution in detectable ways. Now let us consider something that connects the monopoly problem to another great mystery of the universe: dark matter. Dark matter constitutes approximately 27% of the total mass energy of the universe. It does not emit, absorb, or reflect light. It interacts with ordinary matter primarily through gravity. Despite decades of searching, nobody knows what it is made of. Various candidates have been proposed, including weakly interacting massive particles, axions, primordial black holes, and others. Could magnetic monopoles be dark matter? The idea is not unreasonable at first glance. Monopoles are massive. They interact very weakly with ordinary matter at large distances because their magnetic fields fall off like any other dipole from far away. Only up close does their monopole nature become apparent. And if inflation did not dilute them completely, a residual population could contribute to the cosmic mass budget. However, careful analysis shows that monopoles are unlikely to constitute all or even most of the dark matter. The constraints from the Parker bound and neutron star heating are too stringent. If monopoles were abundant enough to explain dark matter, they would drain galactic magnetic fields too quickly and heat neutron stars too much. The observations rule out monopoles as the primary dark matter candidate. This does not mean monopoles play no cosmological role at all. A small subdominant population of monopoles could exist without violating any observational constraints. They would be too rare to detect as dark matter, but could still have interesting effects, perhaps catalyzing proton decay in certain environments, or producing subtle signatures in primordial nucleosynthesis. Let us now address a question that has been growing in the background throughout our discussion. What if monopoles simply do not exist? What would that mean for physics? If monopoles definitively do not exist, if we could somehow prove a negative with absolute certainty, it would have several major implications. First, Dirac's explanation for charge quantization would fail. We would need to find another reason why electric charge comes in exact packets, or accept that it is simply a brute fact of nature with no deeper explanation. Some alternative explanations exist within certain theoretical frameworks, but none are as elegant or as economical as Dirac's monopole argument. Second, grand unified theories in their current form would be in serious trouble. If guts are correct, they predict monopoles. If monopoles do not exist, either guts are wrong or something prevents monopoles from ever forming, which would require new physics beyond what we currently understand. It would force a major rethinking of how the forces unify, if they do at all. Third, the mathematical beauty of electromagnetic duality would be just that. Mathematical beauty with no physical realization. It would be a cautionary tale against letting aesthetics guide physics. Nature would not be obliged to satisfy our sense of elegance. Fourth, the entire chain of reasoning that led from the monopole problem to inflation would need re-examination. If there are no monopolies, there is no monopole problem. And one of the original motivations for inflation disappears. Inflation would still be supported by its solutions to the horizon and flatness problems, and by observations of the cosmic microwave background, so it would not be falsified. But its historical genesis would be based on a non-problem. However, it is extremely difficult to prove that something does not exist. You can search everywhere you know to look and find nothing, but there might always be somewhere you have not looked. Monopoles might be too heavy to produce in our accelerators. They might be too rare to pass through our detectors. They might be hidden in places we have not checked. The absence of evidence, especially for something predicted to be rare, is not the same as evidence of absence. This is why the search continues, decade after decade, with each new technology and each new experimental approach pushing the boundaries slightly further. Now let me tell you about something fascinating that connects monopoles to a completely different area of physics, the quantum Hall effect, and more broadly to the concept of topology in physics. Topology is the branch of mathematics that studies properties that remain unchanged when objects are smoothly deformed. A coffee mug and a donut are topologically equivalent because you can smoothly deform one into the other without cutting or gluing. They both have one hole. A sphere and a cube are topologically equivalent because neither has any holes. Topological properties are robust, stable, and discrete. You cannot have half a hole. You either have a hole or you do not. Magnetic monopoles are topological objects. Their magnetic charge is a topological property of the field configuration surrounding them. This means it is absolutely stable. You cannot smoothly remove the monopole's charge without cutting the field configuration. Just as you cannot remove the hole from a donut without cutting the donut. This is why monopoles, once created, are absolutely permanent. They cannot decay. They cannot lose their charge through any smooth process. They can only disappear by meeting an antimonopoly and annihilating. This topological stability has a beautiful mathematical formulation involving something called homotopy groups. The magnetic charge of a monopole is classified by the second homotopy group of the vacuum manifold of the theory. Different elements of this group correspond to different monopole charges. The group structure ensures that charges combine properly, that monopoles and antimonopoles annihilate correctly, and that certain charges are absolutely conserved. This connection between monopoles and topology has had profound influence on theoretical physics, even beyond the monopole itself. It showed physicists that topology plays a crucial role in quantum field theory. This insight led to the discovery of other topological phenomena, instantons, skyrmions, and eventually the topological phases of matter that have become one of the hottest topics in condensed matter physics over the past 2 decades. The 2016 Nobel Prize in Physics was awarded to David Thouless, Duncan Haldane, and Michael Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter. While this work was not directly about monopolies, it grew from the same mathematical framework. The concept that topology can protect physical quantities and create robust, quantized phenomena traces back through a lineage that prominently features the magnetic monopole. Let us also discuss an aspect of monopoles that is often overlooked but deeply fascinating: their angular momentum properties. When you have both an electric charge and a magnetic monopole present, the electromagnetic field between them carries angular momentum. This is not angular momentum associated with anything spinning. It is angular momentum stored in the electromagnetic field itself, in the crossed electric and magnetic fields between the two charges. This angular momentum has a remarkable property. It is quantized. It comes in half-integer multiples of the reduced Planck constant, just like the spin angular momentum of particles. And here is the truly remarkable part. Even if both the electric charge and the magnetic charge are spinless particles, with no intrinsic angular momentum, the system as a whole has half-integer angular momentum. It behaves as if it were a fermion, a particle with half-integer spin. This means that a composite system of an electric charge and a magnetic monopole, even if both are bosons individually, becomes a fermion. The electromagnetic field itself contributes the half-integer spin. This is called the charge monopole dion, and it demonstrates that the distinction between bosons and fermions is not as fundamental as it might seem. The topology of the electromagnetic field can convert one type of particle statistics into another. This discovery, made independently by several physicists in the 1970s, was one of the early hints that topology and quantum statistics are deeply connected. A connection that has since flourished into a rich area of theoretical physics involving anyons, topological quantum computing, and exotic states of matter. Let us now consider a variation on the monopoly theme, the dion. A dion is a hypothetical particle that carries both electric charge and magnetic charge simultaneously. The concept was introduced by Julian Schwinger in 1969. Dions generalize the monopole concept, and they appear naturally in many theoretical frameworks. In grand unified theories, the spectrum of magnetic objects is richer than just simple monopolies. There are dions with various combinations of electric and magnetic charges. There are bound states of monopolies. There are configurations where multiple monopoles cluster together in specific patterns. The existence of dyons would make electromagnetic duality even richer. Under a duality transformation, a pure electric charge becomes a pure monopole. But what about a dion with both types of charge? Duality mixes dyons with different charge ratios into each other, revealing a complex web of transformations that maps one type of particle into another. In certain supersymmetric theories, the spectrum of dyons can be calculated exactly, and it reveals beautiful mathematical structures involving modular forms. The same mathematical objects that Andrew Wiles used to prove Fermat's last theorem. This unexpected connection between magnetic monopoles and number theory is one of the most surprising and beautiful examples of the unity of mathematics and physics. Now I want to take you deeper into something we touched on earlier, but deserves more attention: the relationship between monopoles and the vacuum structure of quantum field theories. In quantum field theory, the vacuum is not empty. It is a seething quantum state with complex structure. The vacuum can come in different phases, just as water can be liquid, solid, or gas. The phase of the vacuum determines which particles exist, what their masses are, and how they interact. Magnetic monopoles are intimately connected to the vacuum structure. In the confined phase of certain theories, where the force between charges grows with distance rather than diminishing, monopoles condense in the vacuum. They form a kind of magnetic superfluid that fills all of space. This condensation of monopoles is what causes the confining force. This idea, proposed by 't Hooft and others in the 1970s, provides one of the best pictures we have of why quarks are confined inside protons and neutrons. The strong force between quarks can be understood in a dual description as being caused by a condensate of magnetic monopoles in the vacuum. The chromoelectric flux tube between quarks. The string of strong force that pulls them back together if you try to separate them can be seen as a region where the magnetic monopole condensate is expelled, analogous to the Meissner effect in ordinary superconductors, where magnetic fields are expelled. This is called dual superconductivity, and it provides a physical picture of confinement that, while not rigorously proven, is supported by lattice gauge theory simulations and various theoretical arguments. It means that even if fundamental magnetic monopoles are never found as individual particles, they might still be playing a crucial role in the structure of the vacuum that determines the behavior of the strong force. The fact that monopoles might be condensed in the vacuum rather than existing as free particles adds another dimension to the search. You would not detect such monopoles by looking for individual particles because they are part of the vacuum itself, invisible in the same way that the Higgs field is invisible despite being everywhere. Their effects would be seen indirectly in the properties of the strong force and the behavior of quarks and gluons. Let me now share some of the cutting-edge theoretical developments related to monopoles that have emerged in recent years. One exciting direction involves the connection between monopoles and non-perturbative phenomena in quantum field theory. Non-perturbative effects are those that cannot be described by the standard approximation methods of particle physics. They include things like tunneling between different vacuum states, the creation and annihilation of topological defects, and phase transitions in the quantum vacuum. Monopoles are key players in all of these phenomena. In the 1990s, Nathan Seiberg and Edward Witten achieved a breakthrough in understanding certain supersymmetric gauge theories by showing that monopoles becoming light at particular points in the parameter space cause dramatic physical effects. They showed that when monopoles condense, they drive the theory into a confined phase where the electric charges are locked up. This work, known as Seiberg-Witten theory, provided the first exact results for the low-energy behavior of non-abelian gauge theories and revealed a beautiful mathematical structure involving elliptic curves and periods. The Seiberg-Witten solution was a landmark in theoretical physics, because it showed that monopolies are not just exotic curiosities, but central actors in the dynamics of quantum field theories. Their condensation, their interactions, their quantum numbers, all of these play crucial roles in determining the phase structure of the theory. Even in theories without exact supersymmetry, the qualitative lessons from Seiberg-Witten theory are believed to apply, suggesting that monopole dynamics underlies the behavior of the strong force in our own universe. Another modern development involves the connection between monopolies and quantum entanglement. Recent work has shown that the topological properties of monopolies are connected to patterns of quantum entanglement in the vacuum. When a monopole is present, the pattern of entanglement in the surrounding quantum fields is modified in a specific, calculable way. This has implications for quantum information theory and for our understanding of how information is stored in quantum fields. There is also ongoing work on what are called non-abelian monopolies, generalizations of the Dirac monopole that carry charges under non-abelian gauge groups, like the color group of the strong force. These objects are more complex than simple magnetic monopolies. They have internal degrees of freedom, they can transform under gauge rotations, and their interactions with each other and with ordinary matter are richer and more varied. Understanding non-abelian monopolies is believed to be key to understanding confinement in the strong force. Let me also tell you about a recent and fascinating development connecting monopolies to quantum computing. In certain topological phases of matter, excitations called non-abelian anyons can exist. These are particles that, when you braid them around each other, enact quantum logic operations on the quantum state of the system. This braiding can be used to perform quantum computations that are inherently protected against errors by the topological nature of the operations. Magnetic monopole-like excitations in certain lattice models can behave as non-abelian anyons. Their topological stability and their non-trivial braiding statistics make them ideal carriers of quantum information. While this application involves emergent monopolies in condensed matter systems rather than fundamental monopolies in empty space, it demonstrates that monopole physics has practical technological implications beyond pure fundamental science. Now let us explore one more deep connection: the relationship between magnetic monopolies and black holes. In 1916, Hans Reissner and Gunnar Nordstrom independently found the solution to Einstein's equations of general relativity for a charged, non-rotating black hole. This Reissner-Nordstrom solution describes the space-time geometry around a black hole carrying electric charge. There is an exactly analogous solution for a black hole carrying magnetic charge. A magnetically charged black hole is a perfectly valid solution to the equations of physics. It carries a magnetic monopole charge that would be detectable from outside the event horizon through the magnetic field it produces. Could magnetic monopoles exist as extremal black holes? An extremal black hole is one where the charge is the maximum possible for a given mass, balanced precisely at the threshold between a black hole with a normal event horizon and a naked singularity. Extremal magnetically charged black holes have remarkable properties. They have zero temperature. They do not evaporate through Hawking radiation. They are absolutely stable. In string theory, extremal black holes with both electric and magnetic charges have been a powerful testing ground for understanding quantum gravity. The entropy of these black holes, calculated from their geometric properties using the Bekenstein-Hawking formula, matches exactly with a statistical count of microscopic states in string theory. This matching, achieved by Andrew Strominger and Kumran Vafa in 1996, was one of the greatest successes of string theory and provides strong evidence that string theory correctly describes the microscopic structure of black holes. Monopolies played a crucial role in this achievement. The microscopic states being counted are configurations of D-branes that carry monopole charges. The entire calculation relies on the properties of monopolies in string theory. Once again, even if fundamental monopolies are never found as free particles, their theoretical properties have been essential for advancing our understanding of quantum gravity. There is another fascinating connection between monopolies and black holes involving something called the weak gravity conjecture. This conjecture, proposed by Nima Arkani Hamed, Lubos Motel, Alberto Nicolis, and Kumran Vafa in 2006, states that in any consistent theory of quantum gravity, there must exist a particle whose charge-to-mass ratio exceeds a certain bound. Applied to magnetic charge, this conjecture implies that there must exist magnetic monopolies lighter than a specific mass determined by the magnetic coupling constant. The weak gravity conjecture, if correct, would strengthen the argument for monopole existence from a completely different angle. It would say not just that monopolies can exist, or that certain theories predict them, but that any universe with quantum gravity must contain them. Their existence would be demanded not by grand unification or by the Dirac argument, but by the consistency of gravity at the quantum level. This conjecture remains unproven in full generality, but it has accumulated significant evidence from string theory constructions and from general arguments about black hole physics. If it is correct, monopoles are not just probable, but inevitable in any universe that includes both quantum mechanics and gravity, which is to say in our universe. Let us now consider what it would actually mean, practically and theoretically, if a magnetic monopole were discovered tomorrow. Imagine a scenario where the Moidal detector at the LHC finds unmistakable evidence of a monopole produced in a proton-proton collision. Or imagine that a new generation of superconducting loop detectors registers multiple, reproducible monopole passages. What happens next? First, the immediate impact on fundamental physics would be seismic. The discovery would confirm the Dirac quantization condition and finally explain why electric charge comes in discrete units. 100-year mystery solved in one stroke. Every textbook on electromagnetism would need a new chapter. Maxwell's equations would gain their missing terms, becoming fully symmetric. Second, measuring the mass and magnetic charge of the monopole would immediately constrain which theories of physics beyond the standard model are correct. If the monopole is light, around the TV scale accessible at the LHC, it would point towards certain extensions of the standard model. If it is much heavier, in the gut range. It would confirm grand unification and tell us about physics at incredibly high energy scales. The properties of the monopole would be a window into physics at energies we could never hope to reach directly. Third, the discovery would have implications for cosmology. If monopolies can be produced at accessible energies, the story of their production and dilution in the early universe would need to be recalculated. The relationship between the gut phase transition, monopole production, and inflation would be sharpened and tested. Fourth, and perhaps most speculatively, the discovery could eventually lead to new technologies. A particle carrying isolated magnetic charge would interact with magnetic fields in unprecedented ways. It could potentially be used in new types of accelerators, new types of detectors, new ways of manipulating magnetic fields at the quantum level. The history of physics is replete with examples of fundamental discoveries leading to transformative technologies that nobody could have predicted. From the electron to electronics, from quantum mechanics to lasers and semiconductors. Who knows what magnetic charges might enable? But we must be honest about the current state of affairs. Despite all the theoretical reasons to believe in monopolies, despite the beauty of the mathematics, despite the elegance of Dirac's argument, despite the inevitability of gut monopolies, despite the hints from condensed matter physics, we have not found one. Not one confirmed detection in nearly a century of searching. What should we make of this? One perspective is patience. The theoretical framework is strong and self-consistent. Inflation explains why monopolies should be incredibly rare. The experimental challenge is enormous. We may simply need better technology, bigger detectors, higher energy colliders, longer observation times. The history of physics is full of particles predicted long before they were found. The neutrino was predicted in 1930 and not detected until 1956. The Higgs boson was predicted in 1964 and not found until 2012. The gravitational wave was predicted in 1916 and not directly detected until 2015. Patience has been rewarded before. Another perspective is more cautionary. At what point does a prediction without confirmation become a failed prediction? If monopolies are never found despite increasingly stringent searches, at what point do we conclude they probably do not exist? There is no clear answer to this question, and reasonable physicists disagree. Some argue that the theoretical arguments are so compelling that monopolies should be searched for indefinitely. Others argue that the absence of evidence, while not proof of absence, should gradually shift our confidence toward non-existence as more and more parameter space is ruled out. A third perspective takes a broader view. Whether or not monopolies are found, the theoretical work they have inspired has been transformative for physics. The study of monopolies led to inflation. It led to deep insights about topology in quantum field theory. It led to exact solutions of strongly coupled theories. It led to understanding of confinement. It contributed to progress in quantum gravity through black hole entropy counting. It inspired the discovery of topological phases of matter. The monopole, even if it remains forever undetected, has been one of the most productive ideas in theoretical physics. Its value lies not only in its potential existence, but in what thinking about it has taught us about the structure of the physical world. Now let me bring us to one final, deep point about what the monopole question really asks us. At its heart, the question of the magnetic monopole is a question about the relationship between mathematics and reality. Physics is unique among the sciences in its deep reliance on mathematical beauty as a guide to truth. Again and again, equations that physicists found beautiful turned out to describe nature. Dirac's equation, aesthetically motivated by combining quantum mechanics and relativity in the most elegant way possible, predicted antimatter. Einstein's general relativity, motivated by the beautiful idea that gravity is geometry, predicted gravitational waves and black holes. The standard model of particle physics, built on the elegant mathematical framework of gauge symmetry, predicted particles like the W boson, the Z boson, and the Higgs boson before they were found. These successes have led to what physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. Mathematics seems to know about the physical world in advance, as if the universe is constructed along mathematical lines that we can discover through pure thought. The magnetic monopole is perhaps the ultimate test of this faith. The mathematics is clear. Electromagnetic duality demands symmetry between electric and magnetic charges. Dirac's quantization argument shows that monopolies solve the charge quantization puzzle. Grand unified theories inevitably produce them. The weak gravity conjecture may require them. Every theoretical signpost points toward their existence, and yet nature refuses to show them to us. The experiment, the ultimate arbiter of physical truth, has returned nothing but silence on this question for over 90 years. Is this silence temporary, a consequence of inflationary dilution and our limited experimental capabilities? Or is it permanent, a message from nature that mathematical beauty is sometimes a mirage, that not all elegant possibilities are realized, that the universe is not obligated to satisfy our aesthetic sense? We do not know. And this uncertainty, this tension between the compelling logic of theory and the stubborn silence of experiment, is exactly what makes the magnetic monopole one of the deepest open questions in all of physics. The universe may have one final surprise in store for us. Perhaps the next generation of experiments will find a monopole and vindicate decades of theoretical prediction. Perhaps we will find something even more unexpected, a new kind of magnetic object that nobody predicted. Or perhaps the silence will continue indefinitely, and we will have to accept that the universe, while mathematical, is not obligated to realize every mathematical possibility. Whatever the answer, the search for the magnetic monopole teaches us something profound about the nature of scientific inquiry. It is not enough to have a beautiful theory. It is not enough to have compelling mathematical arguments. In the end, nature speaks through experiment, and we must listen, however surprising or disappointing the message might be. Let us now step back even further and consider the magnetic monopole within the grand landscape of unsolved problems in physics, because its connections run deeper and wider than you might expect. The Standard Model of particle physics is the most successful scientific theory ever constructed, in terms of the precision of its predictions and the range of phenomena it describes. It accounts for 3 of the 4 fundamental forces and all known elementary particles. Its predictions have been confirmed to extraordinary accuracy, in some cases matching experiment to 12 decimal places. And yet the Standard Model is clearly incomplete. It does not include gravity. It does not explain dark matter or dark energy. It does not explain why there are 3 generations of particles, why particles have the masses they do, why the fundamental constants take the values they do. It does not explain the matter-antimatter asymmetry of the universe. And it does not contain magnetic monopolies. Many of these unsolved problems might be connected to each other, and monopolies sit at several of these connections. Consider the strong CP problem. This is the puzzle of why the strong nuclear force respects a symmetry called CP when there is no theoretical reason it should. The most popular solution involves a new particle called the axion. And axions have interesting interactions with magnetic monopolies. The Witten effect, discovered by Edward Witten in 1979, shows that in the presence of a theta angle, a magnetic monopole acquires a fractional electric charge. This means that the solution to the strong CP problem directly affects the properties of monopolies, and vice versa. Finding a monopole and measuring whether it carries a fractional electric charge would directly probe the physics of the strong CP problem. Consider the hierarchy problem. This is the puzzle of why the Higgs boson mass is so much smaller than the Planck mass, the natural scale of quantum gravity. Various solutions have been proposed, including supersymmetry, extra dimensions, and compositeness. Each of these solutions makes different predictions for the properties of magnetic monopolies. Supersymmetric monopolies have special properties. They come in supermultiplets. They satisfy certain mass bounds. They have fermionic zero modes. Monopolies in extra dimensions can wind around the compact dimensions in various ways, leading to a rich spectrum of masses and charges. Finding a monopole and measuring its properties would potentially distinguish between these different approaches to the hierarchy problem. Consider dark energy. This is the mysterious force causing the expansion of the universe to accelerate. Some theoretical models of dark energy involve phase transitions in the recent universe, analogous to the gut phase transition in the early universe. If such transitions produce topological defects, there might be monopolies being produced even today, at cosmological rates too low to detect locally, but potentially influencing large-scale cosmic evolution. Consider the matter-antimatter asymmetry. The universe contains far more matter than antimatter, but the Standard Model cannot explain why. The gut processes that produce monopolies are closely related to the processes that could produce this asymmetry. In some gut models, the same phase transition that creates monopoles also creates the baryon asymmetry through a process called gut baryogenesis. Understanding monopole production is therefore intimately connected to understanding why we exist at all. These connections are not coincidental. They arise because monopoles are tied to the deepest structural features of quantum field theory. To gauge symmetry, topology, duality, and unification. They are not just another particle to be discovered. They are a probe of the architecture of physical law itself. Let me now discuss the future experimental landscape in more detail. Because despite decades of null results, the search for monopoles is very much alive and entering a new era. The high-luminosity upgrade of the Large Hadron Collider, scheduled to begin taking data within this decade, will increase the rate of proton-proton collisions by a factor of 5 to 7 compared to the current LHC. This means the Moedal experiment and its successor, Moedal map, will accumulate much more data, probing deeper into the possible mass range of monopoles. If monopoles with masses up to several TeV exist and can be produced in pairs, the high-luminosity LHC should be able to produce and detect them. Beyond the LHC, there are proposals for future colliders with even higher energies. The future circular collider proposed by CERN would collide protons at energies up to 100 TeV, 7 times higher than the LHC. A collider in China, the Circular Electron-Positron Collider, is also being planned with future proton-proton capabilities. These machines would extend the mass reach for monopole production significantly. But colliders are not the only frontier. New detector technologies are being developed for direct monopole searches. Advanced squid arrays with multiple superconducting loops could achieve much greater sensitivity and area coverage than Cabrera's original experiment. Large area nuclear track detector deployments could survey enormous volumes of matter for trapped monopoles. New quantum sensing technologies based on nitrogen vacancy centers in diamond and other systems might achieve sensitivity to even weakly interacting magnetic objects. There are also proposals for space-based monopole detectors. Placing a detector in orbit or on the lunar surface would avoid the shielding effect of Earth's magnetic field, which might deflect incoming monopoles, and would provide access to a different population of cosmic monopoles. The LISA Pathfinder technology, developed for gravitational wave detection in space, includes inertial sensors that could in principle be adapted for monopole detection. Another intriguing approach involves ancient mineral detectors. Certain minerals, particularly muscovite mica, preserve damage tracks from heavily ionizing particles for billions of years. A monopole that passed through a mica crystal a billion years ago would have left a track that can be revealed by chemical etching today. The advantage of this approach is the enormous exposure time, millions or billions of years, compensating for the low expected flux. Researchers have examined mica samples and set limits on the ancient monopole flux, but the technique could be pushed further with newer samples and better analysis methods. The IceCube Gen 2 experiment, a major upgrade of the South Pole neutrino detector, will increase the instrumented volume of Antarctic ice enormously. This will improve sensitivity to relativistic monopoles passing through the detector, complementing the low-energy monopole searches at accelerators. Perhaps most exciting are the novel theoretical ideas about where monopoles might be hiding that have emerged in recent years. Some researchers have proposed that monopoles might be bound into monopoly-anti-monopole pairs called monopolium. Bound states held together by the magnetic force between opposite magnetic charges. These bound states would be electrically neutral and magnetically neutral from a distance, making them very difficult to detect. They could be created in the early universe and persist today as an invisible population. Specialized searches for the radiation emitted when monopolium states transition between energy levels have been proposed. Others have suggested that monopoles might exist in a confined phase, where they cannot exist as free particles, but only in bound states. This would be analogous to quarks, which carry color charge but are never found in isolation. If monopolies are confined, the search strategy would need to change completely. Instead of looking for individual monopolies, we would look for their indirect effects on low-energy physics. Yet another possibility is that monopolies have exotic charges under additional symmetries that cause them to decay rapidly after production, leaving only their decay products rather than stable monopolies for detection. In this scenario, the signature would be unusual events in collider experiments with distinctive kinematic properties rather than a long-lived heavy particle. The diversity of these ideas shows that the theoretical community has not given up on monopolies, but is rather expanding the range of possibilities for how they might manifest. Let me now talk about something that I think is philosophically important about the monopole search. It concerns the relationship between different types of evidence and different levels of confidence. In physics, we distinguish between different levels of confidence in a claim. At the lowest level, we have speculation, ideas that are interesting but lack both theoretical derivation and experimental support. Above that, we have theoretical prediction, claims derived from well-established principles but not yet tested. Above that, we have indirect evidence, experimental results that are consistent with the prediction and difficult to explain otherwise. And at the top, we have direct detection, unambiguous experimental confirmation. Where do magnetic monopolies sit on this scale? They are much more than speculation. They are derived from well-established principles of quantum mechanics and gauge theory by multiple independent arguments. They are predicted by our best theories of unification. They are consistent with everything we know about the structure of matter and forces. By any measure, they are among the most well-motivated predictions in theoretical physics. But they lack direct detection. They lack even strong indirect evidence. They exist in a peculiar position, robustly predicted by theory but stubbornly absent from experiment. This position is not unique in physics. Gravitational waves spent a century in this position before their detection in 2015. The Higgs boson spent half a century there before 2012. Neutron stars were predicted decades before they were observed. In each of these cases, the theoretical prediction was eventually vindicated, and the delay was due to experimental limitations rather than any flaw in the theory. But there are also cases where robust theoretical predictions have not been vindicated. Proton decay, predicted by grand unified theories with specific lifetime estimates, has not been observed despite decades of searching. The lightest supersymmetric particle, predicted by many extensions of the Standard Model, has not been found at the LHC despite searches in the expected mass range. These null results do not definitively rule out the predictions, but they push the theories into less natural regions of parameter space and reduce confidence. Monopolies occupy an intermediate position. They are not as directly constrained as proton decay, because inflation provides a natural explanation for their rarity. But they are also not as close to detection as gravitational waves were in the decades before LIGO. They remain genuinely open, a question mark at the heart of fundamental physics. This is what makes them so compelling as a subject of study. They force us to confront deep questions about the methodology of science, about how we weigh theoretical beauty against experimental silence, about how long we should persist in a search before drawing conclusions. These are not just questions for physicists. They are questions for anyone who thinks about how we come to know things about the world. Let me now bring us into one of the most profound aspects of this entire story, one that often gets lost in the technical details. The magnetic monopole question ultimately asks us, what is a force? We talk about the electromagnetic force, the strong force, the weak force, the gravitational force. But what are forces, fundamentally? In modern physics, Forces are described by gauge theories. A gauge theory is a theory with a special type of symmetry, a gauge symmetry, which dictates the properties of the force. The electromagnetic force corresponds to a U-gauge symmetry. The weak force corresponds to an SU gauge symmetry. The strong force corresponds to an SU gauge symmetry. Magnetic monopolies are defects in the gauge symmetry. They are points where the gauge field configuration is topologically non-trivial, where the abstract internal space of the gauge symmetry is twisted in a way that cannot be untwisted without creating a singularity. They are windows into the topology of the space of all possible force configurations. Finding a monopole would be finding a defect in the force. Not in the metaphorical sense of a flaw or an imperfection, but in the precise mathematical sense of a topological defect. A place where the usual smooth description of the force breaks down and something qualitatively new emerges. This is why monopolies are so much more than just another particle to add to the catalogue. They are not like discovering a new quark or a new lepton, additions to an existing framework. They would represent a fundamentally new type of object, a new way for matter and force to be organized. They would be the first topological particle ever discovered in the context of fundamental physics. They would validate the idea that topology, the mathematics of global structure and connectivity, plays a direct role in determining what particles exist in our universe. This brings us to a profound connection with the concept of emergence in physics. We have already discussed how spin-ice systems produce emergent monopolies, but the relationship between emergence and fundamental physics is deeper than this example suggests. Some physicists have proposed that all particles might be emergent. Perhaps there is no truly fundamental level. Perhaps what we call elementary particles, electrons, quarks, photons, are themselves emergent excitations of some deeper substrate, just as spin-ice monopolies emerge from the collective behavior of atoms. If this is true, then the distinction between fundamental monopolies and emergent monopolies might be less meaningful than we think. The important thing would not be whether a monopole is fundamental or emergent, but whether it exists and what it tells us about the underlying structure. This philosophical perspective has gained traction in recent years through developments in quantum gravity and the holographic principle. The holographic principle suggests that the degrees of freedom of a gravitational theory in a certain volume of space can be described by a non-gravitational theory living on the boundary of that volume. In this framework, what appears as a spatial dimension in one description is an emergent phenomenon in the other. Particles that appear fundamental in the bulk of space might be composite in the boundary description, and vice versa. In holographic frameworks, monopolies often play crucial roles. They appear as specific configurations in the boundary theory that correspond to particular objects in the bulk gravitational theory. The duality between electric and magnetic charges in the bulk gets mapped onto specific dualities in the boundary theory. Understanding monopolies in these holographic contexts is essential for understanding how space-time itself might emerge from more fundamental quantum information. Now let us come back from these theoretical heights and consider something more concrete. What practical consequences would monopole discovery have? We have already mentioned the possibility of new technologies based on isolated magnetic charges. But let us think about this more carefully. What could you actually do with a monopole? First, you could use it to directly test fundamental physics at extreme precision. The Dirac quantization condition predicts an exact relationship between electric and magnetic charge. Measuring both on a single monopole would test this relationship. Any deviation, however small, would indicate new physics beyond our current understanding. This would be a precision test of quantum mechanics and gauge theory of a type that has never been possible before. Second, monopolies could be used as probes of extreme environments. Because monopolies interact with magnetic fields so strongly, they would be accelerated to enormous energies by astrophysical magnetic fields. A monopolar detector in space could detect monopoles accelerated by the galaxy's magnetic field, effectively using the entire galaxy as a particle accelerator. The energy of these monopoles would probe physics at scales far beyond terrestrial experiments. Third, there are speculative but fascinating ideas about using monopoles for energy generation. A monopole oscillating in a magnetic field would generate electric current, similar to how an electric charge oscillating in an electric field radiates energy. The enormous magnetic charge of a monopole means it would couple extremely strongly to magnetic fields, potentially allowing efficient energy extraction from ambient magnetic fields. Fourth, monopoles could enable new types of magnetic materials and devices. Currently, all magnets are dipoles, with coupled north and south poles. A material containing monopoles would be qualitatively different. A magnetic conductor where magnetic charge can flow, just as electric charge flows in metals. The properties of such a material would be unprecedented. These are speculations, of course. We cannot know what technologies would follow from monopole discovery any more than scientists in 1897, upon discovering the electron, could have predicted the internet. The history of science shows that fundamental discoveries lead to applications that are completely unforeseeable. The important point is that monopoles, if found, would open an entirely new chapter in physics and potentially in technology. But let us also consider the other side. What if monopoles are never found? What does this mean for the edifice of theoretical physics that predicts them? If monopoles are not found despite increasingly powerful searches, several responses are possible. The most conservative is to continue invoking inflationary dilution. As long as inflation is viable as a cosmological theory, it can always explain why monopoles are too rare to detect. This is logically valid, but has a whiff of unfalsifiability about it. A prediction that can always be saved by saying the thing exists, but is too rare to find, is difficult to distinguish from a prediction that is simply wrong. A more radical response would be to revisit the assumptions underlying monopole predictions. Perhaps the gut phase transition happened differently than we assume. Perhaps the topology of the gauge group is different from what we think. Perhaps there are mechanisms that destroy monopoles after they form, annihilating them efficiently in the early universe. Each of these possibilities is worth exploring and would lead to new physics. Another response involves questioning whether grand unification happens at all, at least in the simple way currently envisioned. Perhaps the forces approach each other at high energies, but never fully unify. Perhaps unification occurs in a higher dimensional context, where the usual topological defect arguments do not apply. These are viable theoretical directions that are actively being explored. The most philosophically radical response would be to question the inference from mathematical possibility to physical existence. Just because something is mathematically consistent does not mean the universe realizes it. Mathematics contains many beautiful structures that have no counterpart in physics. Perhaps electromagnetic duality, while mathematically valid, is simply not a feature of our particular universe. Perhaps our universe is less symmetric than the mathematics allows, and we must accept this as a brute fact rather than demanding an explanation. Each of these responses carries lessons about the nature of scientific reasoning, about the proper weight to give to theoretical beauty, about the relationship between mathematics and reality. The monopole question, precisely because it remains unresolved, forces us to confront these foundational issues more directly than a resolved question ever could. Let us now discuss one more fascinating aspect of monopole physics that deserves attention: the concept of magnetic charge in non-abelian gauge theories and its connection to quark confinement. We mentioned earlier that the confinement of quarks might be understood through the dual superconductivity picture. where magnetic monopoles condense in the vacuum. Let us explore this idea more fully, because it connects the monopole question to one of the 7 Millennium Prize problems in mathematics, the Yang-Mills mass gap problem. The strong force is described by quantum chromodynamics, a gauge theory based on the SU symmetry group. Unlike electromagnetism, which is based on the simpler U group, the SU theory is non-abelian, meaning its force carriers interact with each other. This self-interaction makes the theory incredibly complex and is responsible for confinement. The phenomenon that quarks are never observed in isolation. The mechanism of confinement remains one of the deepest unsolved problems in theoretical physics. We know from numerical simulations on supercomputers that confinement occurs. We can compute its consequences to high precision. But we do not have a satisfying analytical understanding of why it happens. The dual superconductivity hypothesis proposes that confinement occurs because the QCD vacuum contains a condensate of chromomagnetic monopoles carrying color magnetic charge. In ordinary superconductivity, electric charges condense into Cooper pairs, and this condensation expels magnetic fields from the superconductor. By electromagnetic duality, if magnetic charges condense, they would expel electric fields. In the dual superconductor picture, chromomagnetic monopoles condense in the QCD vacuum, expelling chromoelectric flux. This forces the chromoelectric flux between quarks into narrow tubes rather than spreading out. The energy stored in these flux tubes grows linearly with their length, meaning it costs infinite energy to separate quarks to infinite distance. This is confinement. Evidence for this picture comes from lattice QCD simulations. Researchers have identified monopole-like configurations in the gauge fields computed on the lattice, and shown that these configurations correlate strongly with confinement properties. When these monopole configurations are artificially removed, confinement disappears. When they are present, confinement is robust. This is compelling numerical evidence, though not a rigorous analytical proof.